So this is the Endothermic, Exothermic 5.4 additional chemistry workbook. So some of this you will have started in class and you've been given it for homework to finish. So the first question is looking at hot cans are designed to heat food inside them when it's eaten. The heat is generated by mixing the calcium oxide with the water. The diagram shows a cross-section of the hot can. During a trial reaction, the temperature reached 50 degrees, but a temperature of 70 is needed to heat the food properly. Suggest a change that could be made and explain how this could lead to reaching a higher temperature. The water and the calcium oxide need to mix. You have to shake the hot can for a larger temperature increase. You need to change the surface area. If you don't increase the surface area, the particles aren't going to react. The second part of this question then says, when reaction takes place, the bonds are broken and new bonds are formed. Explain in terms of bond breaking and making why some reactions are exothermic. This is obviously an exothermic reaction for it to heat up the food. More bond energy is required to break the bonds in the reactants than is required to form the new bonds in the product. This is why heat energy is released into the surroundings, hence you can heat up the food. Second question then on this paper is a 6-mark question. So it's asking you to show, you explain using the bond energies and the formation of hydrogen chloride is exothermic. So the first thing I did was work out the bonds in the reactants, which would have given me 6, 7, 8. Then worked out the bonds in the products. Remember, you've got 2 of that bond. Then did reactants minus products. Remember that, reactants minus products. And that would give you minus 184. Exothermic because the temperature has increased. You could have written, which might have expanded your answer, more energy in the products than there is in the reactants, okay? The next question then asks you to look at bond energies and calculating bond energies. So it says the relative bond energies in the reaction are shown in this table. The total energy needed to break the bonds in the reactants is 2459. Calculate the energy needed to break that CC bond. Okay, so what you've got to do is work out the bonds that you already know in the reactants. So you know you've got 1 Br, so you write it down, 1 energy for 1 Br. You also know that you've got 4 of the carbon-hydrogen bond. So you've got 4 of the carbon-hydrogen bond. That in total equals 1,845. Now, you know together the whole thing, all of this gives you 2,459. So all you've got to do essentially is imagine that you were adding them together. So you don't know what that bond is, but the rest of the bonds equal that. Take them away from each other, and that will give you what you don't know, which would be 614. It then says total energy released in the bonds in the products formed is 2551, and calculate the energy released when forming the C bond. Exactly the same thing. So you know that you have got 2 Cr bonds. So you know you've got 2 Cr bonds. Look for it on there. And work that out using your calculator. You know you've also got 1, 2, 3, 4 CH bonds. So carry that number down there. So that equals that. All together, it equals that. To find out that remaining bond, you've got to do the total minus what you've worked out, and that is 347. On the reaction profile, use the arrows to label activation energy and the overall energy change. This is in your book. You practice it. Activation energy is that hump. Whenever you see that hump, it's activation energy. Energy change then is the difference, and you could label it on here, between the reactants and the products. That's the overall energy change. Another question, quite nice, laid out. Calculate the energy needed to break the bonds in the reactant. So you have got 1 of the NN triple bond, so that's 249. You could cross that out if you wanted to. You've then got 3 of the HH bond, so 3 of them. Times it together and then add that all together, and that should give you 2 249. Calculate the energy released when all the bonds in the products are formed. Exactly the same thing. You have got 6 if you wanted to count them of the NH bond. So 1, 2, 3, 4, 5, 6. If you were going to count them, times by 6, and there's your answer. It then goes on to ask you to work out the overall energy change. It goes on to ask you to work out the overall energy change, which is reactants minus products. So you do 2249, take away 2346, which should give you minus 97. So it's an exothermic reaction. Overall energy change is negative. Again, the same type of question, asking you to work out the total energy needed to break the bonds in the hydrogen molecules and the nitrogen molecules. So exactly the same thing. As you can see, it's the exact same question as before. As you can see, I made a slight mistake here. So it is reactants minus products. So it's 2249, take away 2346, and that should give you negative 97. So it is a exothermic reaction. Okay, actually exactly the same numbers as the question before. This question then goes on to ask you, so if it's exothermic, to draw out the exothermic energy profile and have a look at the results table. So the table below shows percentage yield of ammonia under different pressures and temperatures. State what happens to the yield of ammonia as you increase the temperature. So you're just looking at the data, you don't really need to know what's going on. As you increase the temperature, so it goes up, you have got a lower percentage yield of ammonia. One manufacturer carried out the Haber process at 200 atmospheres per pressure, 450 degrees, underlie the appropriate or approximate percentage yield of ammonia formed under these conditions. So if you are using 200 atmospheres of pressure and roughly 450, so you're looking between these two numbers, so the number between them is 30.